What if I told you that scattered throughout our galaxy are objects so dense that a single teaspoon of their material would weigh more than Mount Everest? Objects spinning hundreds of times per second, generating magnetic fields a quadrillion times stronger than Earth's. Objects where the laws of physics as we know them collapse into something alien, something that shouldn't exist. These objects are real. They're called neutron stars, and they represent matter pushed to its absolute breaking point, the edge of what the universe will tolerate before reality itself tears apart. Imagine crushing our entire sun, 1,000,000 Earths, down to the size of Manhattan. The atoms themselves disintegrate. Protons and electrons merge. What remains defies every intuition we have about how matter behaves. Today, we journey through evidence that challenges everything we thought we understood about the fundamental nature of reality. We'll witness physics operating at its most extreme limit, where the difference between matter and energy blurs, where time itself warps into strange geometries, and where the universe reveals secrets that border on the impossible. Prepare yourselves. We begin. In 1967, a graduate student at Cambridge University made a discovery that would revolutionize our understanding of the cosmos. Jocelyn Bell Burnell was analyzing radio telescope data when she noticed something extraordinary, a signal pulsing with impossible precision. Every 1.337 seconds, like clockwork, a burst of radio waves reached Earth from deep space. The signal was so regular, so precise, that Bell Burnell and her advisor, Anthony Hewish, half-jokingly called it LGM-1, Little Green Men 1. Could it be an alien beacon? But as more of these pulsing sources were discovered across the sky, a more astonishing explanation emerged. These weren't aliens, they were the corpses of dead stars. When a massive star, 8 to 20 times the mass of our Sun, exhausts its nuclear fuel, it dies catastrophically. The core collapses in less than a second. The outer layers explode outward in a supernova bright enough to outshine an entire galaxy. But what happens to the core? The core continues collapsing. Imagine all the empty space within atoms, and atoms are mostly empty space, being crushed out of existence. The electrons, orbiting far from their nuclei, are forced into the protons at the center. Protons and electrons, normally kept apart by electromagnetic forces, merge into neutrons. What's left is a sphere of neutrons packed so tightly that it becomes essentially a single atomic nucleus the size of a city. A neutron star typically contains 1.4 times the mass of our Sun compressed into a sphere just 20 kilometers across. To comprehend this density, take a sugar cube of neutron star material. It would weigh 100 million tons, as much as the entire human population of Earth. But the discovery raised profound questions. How could such an object exist without collapsing further into a black hole? What prevented gravity from crushing it completely? And why were these objects spinning so impossibly fast? The answers would require us to peer into physics at its most extreme, where quantum mechanics and general relativity collide, where our everyday understanding of matter completely breaks down. But the evidence forces us to confront an uncomfortable possibility that neutron stars represent something far stranger than we ever imagined, something that challenges the very definition of what matter is. The first piece of evidence comes from their rotation. The fastest known neutron star, PSR J1748-2446 AD, spins 716 times per second. At its equator, the surface is moving at approximately 24% the speed of light, 70,000 kilometers per second. Think about that. This is an object with more mass than our Sun, spinning so fast that its surface approaches relativistic speeds. A mountain range on a neutron star, and yes, they have mountains, albeit only millimeters tall, would be flung into space at these speeds if not for gravity so intense that escape velocity approaches half the speed of light. Why do they spin so fast? Conservation of angular momentum. As the stellar core collapses from the size of Earth to the size of Manhattan, it spins faster, just as an ice skater spins faster when pulling in their arms. but the speeds are so extreme that they challenge our understanding of material strength. The second signature, magnetic fields of incomprehensible power. Normal neutron stars possess magnetic fields 1,000,000,000,000 times stronger than Earth's, but a subset called magnetars have fields up to 1,000,000,000,000 times stronger, so powerful they warp the quantum vacuum itself, creating particles from empty space. In 2004, astronomers detected a gamma-ray burst from magnetar SGR 1806-20, located 50,000 light-years away. In 1/10 of a second, this object released more energy than our Sun produces in 100,000 years. If this magnetar were located halfway to our nearest star, Proxima Centauri, its eruption would have stripped Earth's atmosphere and extinguished all life. The magnetic field is so intense that it could kill you from 1,000 kilometers away, not through radiation, but by disrupting the electromagnetic bonds holding your atoms together. The third signature comes from light itself. Neutron stars warp space-time so severely that light bends as it passes near them. In 2019, NASA's NICER telescope observed a neutron star called PSR J0030 plus 0451 and detected something remarkable. Light from the star's backside was visible from Earth, bent around the star by extreme gravitational lensing. The observations revealed the star's exact dimensions, 1.3 times the Sun's mass compressed into a sphere just 25.4 kilometers across. This confirmed theoretical predictions. Neutron stars sit at the absolute edge of stability, held up only by neutron degeneracy pressure, a quantum mechanical effect where neutrons resist being compressed into the same quantum state. But perhaps the most extraordinary evidence comes from their collisions. On August 17, 2017, gravitational wave detectors recorded the merger of two neutron stars 130 million light-years away. For the first time in history, humanity witnessed the creation of heavy elements in real time. Telescopes detected a kilonova, an explosion that forged gold, platinum, uranium, and other elements heavier than iron. Analysis suggested that all the gold in the universe, including the gold in your jewelry and electronics, in Earth's core, was created in neutron star collisions. You are wearing the remnants of stellar catastrophes that occurred billions of years ago. But this is only one piece of a much larger puzzle. As we probe deeper into neutron star physics, we encounter phenomena that seem impossible. The crust of a neutron star is a crystalline lattice of atomic nuclei embedded in a sea of electrons, material 1,000,000,000 times stronger than steel. Beneath this lies a neutron superfluid, a liquid that flows without friction, achieving temperatures where quantum effects manifest at macroscopic scales. Go deeper still into the core, where pressures exceed anything we can create in laboratories, and physics enters unknown territory. Theory suggests we encounter nuclear pasta, matter arranged in bizarre configurations named after Italian cuisine.
Gnocchi, spherical, spaghetti, rod-shaped, lasagna, sheet-like, and anti-spaghetti, tubes of normal matter in a dense medium. This isn't metaphor, it's our best description of matter at densities where atomic nuclei deform and fuse into extended structures stronger than any material in the universe. But even stranger, at the very center, where density reaches twice that of an atomic nucleus, we may encounter a phase transition. Neutrons might dissolve into their constituent quarks, creating quark matter, a state that existed only in the first microseconds after the Big Bang. Recent observations support this possibility. The neutron star at the heart of the supernova remnant Cassiopeia A is cooling far faster than models predict. Why? One explanation, the star has begun converting to quark matter, a process that releases neutrinos and accelerates cooling. If confirmed, this would mean neutron stars aren't just extreme forms of matter we understand, they're laboratories accessing physics we've never directly observed, bridging nuclear physics and particle physics in ways no experiment on Earth can replicate. The evidence extends beyond physics into the realm of space-time itself. General relativity predicts that extreme gravitational fields slow time. On the surface of a neutron star, time runs approximately 30% slower than on Earth. If you could stand on a neutron star, you can't, you'd be crushed and then incinerated, you would age measurably slower than people in distant space. This isn't science fiction. GPS satellites must account for time dilation in Earth's modest gravitational field. On a neutron star, the effect is so extreme that if you watched events unfold in the distant universe, you'd see time accelerated, stars evolving and dying in fast forward. And there's another, more haunting implication. Neutron stars exist at the absolute limit of stability. Add slightly more mass, just 15% more, and gravity overwhelms even neutron degeneracy pressure. The star collapses further, not into a new form of matter, but into a black hole where space-time curvature becomes infinite and our physics breaks down completely. This boundary is called the Tolman-Oppenheimer-Volkoff limit, and we still don't know its exact value. Every observation of neutron stars helps us understand where reality draws the line between matter and oblivion. To understand neutron stars, we must invoke two of humanity's greatest intellectual achievements, general relativity and quantum mechanics. Einstein's general relativity describes how mass warps spacetime, creating what we experience as gravity. Quantum mechanics describes the behavior of particles at the smallest scales, including the Pauli exclusion principle, the law that prevents fermions like neutrons from occupying the same quantum state. Neutron stars exist at the intersection of these theories. Gravity tries to crush the star out of existence. Neutron degeneracy pressure, a purely quantum mechanical effect, pushes back. The battle between these forces creates the extreme conditions we observe. But here's the challenge. General relativity and quantum mechanics are famously incompatible. Einstein's equations assume spacetime is smooth and continuous. Quantum mechanics insists reality is fundamentally uncertain and discrete. Physicists have sought a theory of quantum gravity for nearly a century. Neutron stars may provide the key. Teams at institutions like MIT, Caltech, and the Max Planck Institute are analyzing neutron star observations to constrain the equation of state, the relationship between pressure and density at extreme conditions. Different equations predict different neutron star properties: maximum mass, radius, deformability. When gravitational waves from neutron star mergers were detected in 2017, they revealed how easily the stars deformed before collision, information that ruled out entire classes of theoretical models. Some physicists propose that at the highest densities, new physics emerges. Perhaps quarks themselves dissolve into more fundamental structures. Perhaps strange matter, matter containing strange quarks, becomes stable, transforming neutron stars into strange stars with even more extreme properties. One radical hypothesis: strange matter might be the most stable form of matter in the universe. If so, contact with even a single strange quark could convert ordinary matter into strange matter in a runaway chain reaction, a strange matter catastrophe that could, in principle, convert Earth itself. This almost certainly isn't possible, but the fact that we must consider it reveals how little we understand about matter at these extremes. This forces us to reconsider fundamental assumptions about the nature of matter, the limits of stability, and the boundaries between different states of existence. The era of neutron star astronomy is just beginning. NASA's NICER telescope, mounted on the International Space Station, maps neutron star surfaces with unprecedented precision. By tracking X-ray pulses from hot spots as stars rotate, NICER determines exact sizes and shapes, crucial data for understanding the equation of state. Meanwhile, gravitational detectors, LIGO in the United States, Virgo in Europe, COGRA in Japan, listen for space-time ripples from colliding neutron stars. Each detection refines our understanding. Future detectors like the Einstein telescope and Cosmic Explorer will detect thousands of mergers, revolutionizing nuclear physics. China's 500-meter aperture spherical telescope, FAST, the world's largest radio telescope, is discovering new pulsars at an unprecedented rate. Each new discovery adds data points, mapping the population of neutron stars in our galaxy. On Earth, facilities like the Facility for Rare Isotope Beams, or FRIB, create exotic atomic nuclei to study how nuclear matter behaves under extreme conditions, miniature analogs of neutron star interiors.
Within the next decade, these combined efforts should answer fundamental questions. What is the maximum mass of a neutron star? Does quark matter exist in their cores? How do magnetic fields reach such impossible strengths? Can we detect gravitational waves from star quakes, sudden fractures in neutron star crusts? But the implications extend beyond astrophysics. Neutron star collisions are the universe's alchemical forges, creating most elements heavier than iron. Understanding these collisions tells us about our own origins, the cosmic history encoded in every atom of our bodies. What this means for us is profound. We are literally made of star stuff forged in the most violent events the universe can produce. The calcium in our bones, the iron in our blood, the gold in our technology, all created when neutron stars collided billions of years ago, their debris spreading through space, eventually coalescing into the solar system and life itself. Neutron stars connect us to the cosmos in ways both physical and philosophical. The most profound implications emerge when we consider what neutron stars reveal about reality itself. These objects demonstrate that matter has limits, boundaries beyond which our familiar categories break down. Between neutron star and black hole lies a threshold where matter ceases to exist in any form we recognize, where space-time itself becomes the phenomenon. This raises a question physicists rarely voice. Is matter fundamental, or merely a temporary arrangement of fields and forces? When we peer into neutron star cores, are we seeing matter at its purest, or witnessing its dissolution into something more basic? There's another unsettling possibility. Some theories suggest neutron stars are metastable, existing in a high-energy state that's temporarily stable, but could spontaneously tunnel to a lower-energy configuration. If so, any neutron star could, without warning, undergo a phase transition that converts it entirely to strange matter or triggers collapse to a black hole. The probability is vanishingly small, but in a universe containing billions of neutron stars over timescales of trillions of years, such events become inevitable. Consider, too, the information paradox. When matter crosses a black hole's event horizon, quantum information appears to be lost, violating the laws of quantum mechanics. Neutron stars, existing just shy of this boundary, may hold clues to resolving this paradox. Some physicists speculate that the quantum entanglement between particles in neutron star cores reaches macroscopic scales, creating coherent quantum states involving a trillion neutrons. If so, neutron stars might exhibit measurable quantum effects despite their enormous size, a regime of quantum gravity we've never directly observed. And there's a final, almost mystical consideration. Every neutron star we observe is a time capsule, preserving in its composition the nuclear physics of its parent star, the dynamics of its supernova, the environment of its birth. Some neutron stars formed when the universe was young, when the first massive stars died. They carry information about cosmic conditions 13 billion years ago. In this sense, neutron stars are not just objects, they're witnesses, silent archives of cosmic history stretching back nearly all the way to the Big Bang itself. What we still don't know dwarfs what we do. We don't know if quark matter exists in their cores. We don't know the maximum mass or why magnetars have such extreme fields. We don't fully understand how pulsars emit radiation or why some suddenly glitch, abruptly spinning faster. Each answer spawns new questions, leading us deeper into the strange architecture of reality.
We began with a question. How can objects so extreme, so alien, actually exist? The answer reveals something profound about the universe itself. Neutron stars exist because the universe has rules: quantum mechanics, general relativity, the strong nuclear force, and these rules permit matter to be pushed to its absolute breaking point before surrendering to gravity's final embrace. They are matter's last stand against oblivion, existing in a regime where quantum uncertainty and relativistic gravity dance at the edge of chaos. They forge elements, generate gravitational waves, and illuminate the darkest corners of physics. We know they are real. We can detect them, measure them, learn from them. Yet they remain profoundly strange, challenging our intuitions about what's possible. Perhaps that's the deepest lesson neutron stars offer. The universe is under no obligation to make sense to us. It simply is. Vast, violent, beautiful, and stranger than we imagine,
possibly stranger than we can imagine. But humanity's story is one of reaching beyond our limits, of taking the incomprehensible and making it known. A century ago, we didn't know galaxies existed. Today, we probe the quantum structure of stellar corpses 50,000 light-years away. The universe is vast, the mysteries are endless, the journey continues. And somewhere out there, right now, a neutron star spins 716 times per second, crushing matter into its strangest form, warping space-time around itself, beaming radiation across light-years, a cosmic lighthouse at the edge of possibility, waiting for us to understand.